of you. Actually, in some sense, it is a review of what other people said this morning. And then I will move to what I have to say about it, which is part 3, is an attempt to making sense of Gödel's comments. So I'm starting with Turing's analysis of computability. And in section 9 of his 1936 paper on computable numbers, Turing provides an analysis of the concept of computability. The analysis has attracted much attention in recent years. It was revived by Turing's student Robin Gandhi in the 80s and received a thorough and precise treatment, as we saw this morning, by Wilfried.
Say one thing that I haven't said before somewhere, and I noticed the very well-developed talks everyone else has been giving. Giancarlo Rota says when a mathematician reaches a certain age and attends a meeting, people come just to look at him, not to hear what he says. So perhaps I'll be forgiven. I think I'm probably the oldest person in the room. I want to start by talking a little about the early work of Emil Post when we were the names of Church and Gödel and Kleene and Turing have been mentioned over and over again. Post mentioned occasionally. The early work that he did in the 1920s and that only came to light many years later, I think is interesting in its own right, and as a historical matter is particularly interesting. It's of particular interest to me because he was one of my first real teachers, and I feel a duty to spread that word. Post's dissertation in 1921 contained, among other things, the proof of the completeness and consistency of the propositional calculus. For him, the propositional calculus was the first part of the Whitehead and Russell Principia Mathematica, this 3-volume monster that was then a new thing. In fact, Post was part of a seminar at Columbia University where they actually worked through the whole 3 volumes from beginning to end. It's hard to believe that human beings are capable of even doing such a thing. One of the things he did was to solve what he called the finiteness problem for propositional calculus, what we'd call the decision problem, and that he just used the truth table method, proved that the theorems are the tautologies, and of course it's algorithmic in a very simple way to tell whether something's a tautology. Post wanted to continue. He wanted to to solve the finiteness problem for Principia Mathematica, to algorithmize all of mathematics. But this was clearly the combinatorial complexity of the whole thing was clearly too messy to try to tackle it directly, and so he had the clever idea that he would dissolve the complexity in more general formulations, and that's where his production systems came from that Wilfried mentioned earlier. And it's let me start. I'll push it up later. So in full generality, this was a post-canonical production. Here, sigma is a finite alphabet. Sigma star, this wasn't his notation. Sigma star is the set of all finite strings on the letters of sigma. And a canonical production looks like that terrible-looking thing. Here, the various G's are given strings on the alphabet sigma. The P's are variable strings, non-terminals in the language of language theory. And each of the P's in the following line are each of the P's of the following line are chosen from the ones up above. So the way to think of this is that that what's above the arrow are premises, what follows it is a conclusion, and then his idea was that all of Principia Mathematica, like any similar formal system, could be represented by a finite number of canonical productions of this kind, together with a finite number of given initial strings, sort of axioms, and which, starting with these initial strings and applying the productions and just doing it, you'd get all the theorems. That was his idea. He did certain initial work toward convincing himself that the part of Principia we'd call first-order logic could be reduced to this form, and assumed that there'd be no problem in doing it for the rest of Principia. So he called a system in canonical form, as I explained, a set of initial assertions together with a finite set of these canonical productions. And he considered a much simpler kind of system in which the productions had this particularly simple form. GP becomes PG bar. So instead of a finite set of premises, just one premise. Instead of a bundle of different given G's, just two, a G and a G bar. And the effect of the production is simply to cross off the G at the head and put the G bar on the tail. Okay, now a set of strings is called a canonical string if it's the set of all strings generated by a canonical system. A normal set if it's the set of all strings generated by a normal system. In a normal system, there's just one initial assertion, one axiom. And in 1921, Post proved this reduction theorem. The proof was finally published in 1944. There's another proof in Minsky's book. So let C be a canonical set on an alphabet sigma. Then there's a normal set on a larger alphabet such that the normal set is just the intersection with sigma star of the canonical set. That means now Post had a program. Starting with Principia, he could reduce it to a canonical system. The canonical system could in effect be reduced to a normal system because obviously if you had an algorithm for n, you'd have an algorithm for C. And normal systems looked so simple. All he had to do was solve the decision problem for normal systems, and he set out to do it. And being a good mathematician, he knew that what you should do is start with a simpler case. And there was a particular simpler case that lent itself to him because it came up in connection with what seemed like an entirely unrelated problem as well. It was his problem of tag. This tag systems can be described. I was going to write on the blackboard at this point, but you'll have to settle for a verbal description. Tag systems are a particularly simple kind of normal system. The way they work is start with a string, and you operate by removing a fixed number of characters at the beginning and placing some other characters at the end, and doing this repeatedly according to the following kind of process. Each character, there will be a finite number of characters. Each character has associated with it a particular string, particular finite string. Finitely many characters, each one has a string associated with it. In addition, for a given tag system, there's a particular integer given, let's say 3. For simplicity. So the way the tag system works is you look at the first symbol. There is a string associated with it. You tack that on to the end, and then you strike out the first 3 symbols. Now there's a new symbol on the left. It has a string associated with it. Put that at the end. Cross off the first 3 letters. Okay, so what is the problem of tag? Well, given an initial string, will this eventually terminate? That is, will the whole thing collapse out? Will it become periodic? Will it become unbounded? Those are the possibilities. Minsky proved that this problem is unsolvable many, many, many years later. The Post set out to solve it, and again he started with special cases, and as he worked on these special cases, he found himself getting more and more embedded in messy number theory problems, and this was very upsetting to him, as he put it in what he wrote later. He was expecting to, as it were, dissolve all the complexities of mathematics, including number theory, in the simple combinatorics of these tag systems, and instead, as he began working on them, the number theory kept intruding itself, and there are quite simple tag systems whose properties have never been worked out. People have done computer simulations and so on. Anyhow, he finally made this incredible guess that in fact he was going at it the wrong way, and there really is no solution to the decision problem for Principia, and therefore there isn't any for these normal systems. In fact, he quickly, it turns out these normal sets are just what are called recursively enumerable sets nowadays, and he saw that there is that there are normal sets whose complement are not normal, and so on and so forth. So that's what Post did so long ago. And by the way, he also inferred from this argument that Principia was incomplete for statements involving elementhood in normal sets, because he saw that if it were complete, it would provide an algorithm. So he had both unsolvability results and incompleteness. What he didn't have is Turing's analysis. In other words, he did not have a convincing argument for what he was personally convinced of, namely that every possible algorithmic procedure was already encompassed by these canonical systems. And without it, he then set out on what turned out to be a complete will-o'-the-wisp to try to analyze finite states, all possible, I don't remember his exact words, all possible finite processes, I guess is the way he put it, capable, the human mind is capable of. In effect, he needed Turing's analysis, and he didn't have it, and in the meantime, Gödel came along, and then Church and Turing, and before Turing came on the scene, he independently had essentially the notion of a Turing machine, and actually had independently published his small paper, Finite Combinatorial Combinatory Processes, Part 1. That's the first part. The other thing I wanted to talk about was the relationship between computability theory and actual computation. A topic that Mike Rabin talked about to some extent. I don't. First, I'd like to talk about simply the historical question of the extent to which Turing himself and others at his time thought of what they were doing as having some relation to actual computation and to machines. Turing's 36 paper, I'm sure all of you know this, had the following insights in addition to the theorems that were actually proved. In his own words, he showed that rule of thumb is the same as machine process. Not using his own words, it's implicit in what he did that instructions and data are the same kind of thing. Something which was by no means clear in 1936. It was a radical insight. Hardware, what we call hardware and software, which were in the minds of the engineers in the 30s and early 40s, were entirely different kinds of things. Hardware was something that was a machine that you looked at, and software were these instructions that you might put them on punch cards, or you might execute them by moving cables around, but that's what they were. And then, of course, there was his notion of the universal the universal machine that which provided a model of a memory shared between program and data. And I emphasize that in order to think of such a thing, you also had to be able to think of the program, which in this case has the form of a code for a particular Turing machine. You have to think of it as being the same kind of thing as the data. From my, this is from my popular book that I take the liberty of reading it. Before Turing, here I can do it from here. Before Turing, the supposition was that the three categories, machine, program, data, were entirely separate entities. The machine was a physical object, hardware. The program was the plan for doing a computation. The data was the numerical input. Turing's universal machine showed that the distinctness of these three categories is an illusion. A Turing machine is initially envisioned as a machine, hardware, but its code functions as a program detailing the instructions to the universal machine. Finally, the universal machine and its step-by-step actions sees the machine code as just more data to be worked on. This fluidity is fundamental to contemporary computer practice. A program is data to the compiler. Here is what Church said about Turing in his review in the then almost brand new Journal of Symbolic Logic in 1937. Turing proposes as a criterion that an infinite sequence of digits 0 and 1 be computable, that it shall be possible to devise a computing machine occupying a finite space and with working parts of finite size, which will write down the sequence to any desired number of terms if allowed to run for a sufficiently long time. As a matter of convenience, certain further restrictions are imposed on the character of the machine, but these are of such a nature as obviously to cause no loss of generality. In 1947, at a time when Turing was at the National Physics Laboratory and was quite enthusiastic about the prospects for his ace, he gave an address to the London Mathematical Society, about which is really worth reading just simply for the breadth of vision of what he imagined computers would be able to do and their flexibility. But here I want to indicate how he saw this as related to his earlier work of 1936. Some years ago, I was researching what now may be described as an investigation of the theoretical possibilities and limitations of digital computing machines. Note his description of what he had done in 1936. This type of machine seemed to be sufficiently general, and then I mentioned. Here is more from the same 1947 address. Let us now return to the analogy of the theoretical computing machines. It can be shown that a single special machine of that type can be made to do the work of all. It could, in fact, be made to work as a model of any other machine. The special machine may be called the universal machine. Now, in various discussions, and there have been many, about this relationship and what the results in one area say about the other, there's a key element which seems to be overlooked, ignored, or whatever, and that is that when one is talking about computability theory, recursive function theory, the mathematical subject, the infinity of everything is built in. Algorithms, as they've been understood in mathematical theory and practice over the years, have been thought of always as designed with arbitrary input, ignoring limitations of physical size. The Euclid's algorithm for finding the greatest common divisor of two numbers in no way depends on the size of the integers. There's a sense that every mathematician understands that that algorithm would correctly produce the greatest common divisor of two integers, even if simply to write them down would require more atoms than exist in the entire universe. The physical limitations are simply irrelevant. And the same is true of Sturm's theorem about distribution of real roots of a polynomial equation. And the same is true in the various special cases of the decision problem for first-order logic that have been solved. The algorithms will work for formulas of whatever size. Machines existing on this small planet are a small part of this small planet, are very finite. So the question arises when one starts thinking about that, to what extent is the general theory, which, as I say, has the infinite just built into it, relevant? And I would say to some extent that's an empirical question. Somebody said earlier today that an actual computer is better understood as a finite state machine. Well, there is an obvious physical sense in which that's what it is, but I think it's false that it's better understood that way. In fact, this was a lively debate in the early 1960s. In fact, Elgott and I had an argument about it at a meeting in Brooklyn in the early 1960s when he was making exactly that point. Now, on the face of it, that seems very solid. Who can deny that a computer is a finite object, however complicated? Well, but of course, mathematicians always go to the limit when it's convenient to do it. When you use integral calculus to compute the moment of inertia of some physical object, you in effect assume that it's infinitely divisible. In fact, we know it consists of a finite number of molecules in there, but we ignore that, and the situation is somewhat similar here. If you think about algorithms, it happens to be it's a fact of experience that the algorithms that mathematicians come up with, in fact, don't come up with any bounds on their validity. The algorithm for adding two multi-column numbers that we all learn in elementary school doesn't have any built-in limit. Who doesn't believe that, in fact, if you add two numbers which written down would stretch across the galaxy, that same algorithm would work. Moreover, you see it in algorithmic analysis as it's carried out by computer scientists when they compare two sorting algorithms or whatever. They look at their asymptotic behavior. They say, oh, that's an n log n algorithm. This is an n squared algorithm. The n can be of any size, and they're talking about their behavior as n goes to infinity. Of course, they know perfectly well that the n that they're looking at is going to be bounded by 10 to the 12 at the most. But nevertheless, the asymptotic analysis is thought to be useful. In the same way, you can think of Turing's universal computer modeled by an actual desk computer that you have as very much along the same lines. As I think Professor Shapiro said in his talk, one way to think of the computer as having infinite memory is that you have the capability of just adding additional storage modules as you need them. But of course, this is a dodge. We all know that it's really finite, just as we all know that one day we're going to die, much as we wish the contrary were true. There's been a lot of discussion, some of it mentioned just recently here, about the possibility of physically embodying non-computability in one form or another. And it's important when one talks about that to bear in mind this question of the finite versus the infinite. I have this, Penrose starts his book, to which Mike Rabin referred, by imagining the unveiling of this super AI computer, and I propose analogously to imagine the unveiling of this first hypercomputer. And here it goes, and it is now going to print out for us one after another the digits of a non-computable sequence. Here they come. Here they are. 15, 37, 235. Well, it's been going now for 7 hours, and we got this sequence. Well, of course, it's finite, and therefore it's computable within the focus of computability theory. What would it take for there to be a combination of a physical theory and a physical device that would actually produce something that is uncomputable in a theoretical sense, and not in the sense of just producing something, a finite thing which is Kolmogorov random. That, of course, is perfectly conceivable with present-day physics, but something that is truly as an infinitary object, non-computable? Well, you can perfectly well imagine that there is some physical constant which as a real number is an uncomputable real number, and it might play a role in some physical theory of the future. But what would it take to believe it? Experimental physics as it exists today is very happy with 25 or 26 decimal places. You have to imagine that this is a theory which is so reliable and you believe it so implicitly that you're willing to accept all these digits beyond what is experimentally revealable as being absolutely correct. But who can deny that as an ultimate possibility? It's certainly very remote from anything that exists today. I like to mention that when I wrote my computability and unsolvability book way back in 1948, I said, who can preclude the possibility that someday we might be presented with a black box that would compute an uncomputable function? So I certainly, it would be silly to rule out the device. Now there's, as probably all of you know, there is this current movement called hypercomputation, which proposes all of this as a serious possibility for right now, and I'll mention in a little detail one of the proposals, but some of them really, I mean, one proposal amounts to an exhortation to build an oracle. Another is the trivial observation that if you have a neural net with uncomputable weights, that it will accept uncomputable languages. There's a little bit of an embarrassment de riche. They will accept any language, not just uncomputable ones. But I do want to say a few words about Tien Q's proposal to use quantum mechanics in connection with Hilbert's 10th problem. Now, I have to say, first of all, that I don't consider myself even remotely expert on quantum mechanics, and I will only make the most peripheral remarks. But I think there are some things that can be said that are particularly revealing in this question of the finite versus the infinite. So let me briefly explain. Do I still have a few minutes? So Hilbert's 10th problem has been mentioned before. It's to find an algorithm that will determine a polynomial equation with integer coefficients, whether it has a solution in non-negative integers, and it's been proved to be unsolvable. So Q, a physicist, proposes to use quantum mechanics to solve the problem, and his methods is certainly ingenious. He's going to take the polynomial equation and going to compute the minimum value of its square, and that'll be 0 just in case it has a solution. And the way he does it is to translate the given polynomial into a physical system whose Hamiltonian is related to it in a very simple, striking, formal way. The Hamiltonian is a direct transcription of this p squared. It exists in Fock space, or whatever that is, but the Hamiltonian represents the initial energy of the system. The adiabatic theorem is a theorem in quantum mechanics that tells you that if you transform the system in the appropriate way, it will eventually reach its ground state. I think I'm stating it correctly. And if the equation has a solution, that ground state's going to be 0. Now, I have 2 comments to make. By the way, there's been a lot of definitive discussion of Q's algorithm by people who understand the quantum theory a lot better than I do, but I think these are revealing comments anyhow. So we're going to look at the particular Diophantine equation, x plus 1 squared minus ay squared equals 0. So if a equals a 167, the equation has no solutions because square root of 167 is an irrational number. On the other hand, there are values of a arbitrarily close to 167 for which the equation has solutions. Here is, I've done the silly arithmetic. So if a is instead of 167, this 166 with all those 9s and so on, then there is this integer solution. Thus, in constructing a physical system with a Hamiltonian corresponding to the square of the polynomial, it will be necessary to measure the energy 167 with infinite precision, because it would have to distinguish between these two. In a discussion with Q himself, he commented that no, that's not right, because in quantum mechanics it's all integers. But I'm told by others that that's just not true, that there really is an energy measurement involved, and it has to be done with infinite precision for the thing to work. Now he's giving an alternative. Instead of measuring the energy at the ground state, there's something else you can measure, these things that are called occupation numbers. It doesn't matter what they are. I would like to point out that besides the energy measurement, we can also do with the measurement of occupation number. Such occupation number measurement would give us the positive integers n1, n2, etc., which we can then substitute into the Diophantine polynomial in the places of corresponding variables to see if the polynomial vanishes, in which case the equation has some positive integer solution or not, no solution. So here's his idea. Instead of measuring the energy, you look at these occupation numbers, plug them back into the polynomial, and if it comes out 0, you just do the arithmetic. If it comes out 0, then it has a solution. In fact, that is the solution. Or if it doesn't come out 0, then the equation doesn't have a solution. Sounds great. Now, it's easy to cook up a simple Diophantine equation which has solutions, but the smallest solution couldn't be written down on a blackboard smaller than the size of the galaxy. So he's thinking there's going to be a finite physical apparatus he's going to look at. He's going to plug this polynomial in, get the right Hamiltonian. He'll look at the output and see these numbers that can't even be written down. Then even if he can get hold of them in some way, he's supposed to do the arithmetic. It'll take, the lifetime of the human race just to do the calculation to see whether it comes out to be 0 or not. Anyhow, that's all I wanted to say.
As you mentioned, you said many decades ago in your book that one couldn't, I can't remember the exact words, but one can't rule out the possibility of an alien arriving with some species of machine that could solve an unsolvable problem. And in your talk, you said, imagine a hypercomputer is unveiled, and what must it do in order for us to get to know that it's a hypercomputer? So what did you imagine happening when the alien unveiled the machine that you wrote about all those decades ago?
Goodness, you're asking me what I imagined in the 1950s. I suppose that what I had in mind is that these aliens would so convince us of their superior intelligence and capabilities that we could not bring ourselves to doubt the correctness of what they were telling us. But that's the best I can do.
So, hi. Look, I'm just trying to, I must have at least skimmed your article on Post's account of his work in your volume, The Undecidable. But anyway, I don't have it well in my head. Look, are you claiming on Post's behalf that he actually did formulate a problem, maybe not in arithmetical terms, but in terms of his post system, and showed it undecidable in Principia?
Yeah.
Well, so whether or not he got Turing's ideas, that's a pretty strong anticipation of.
Well, that's his claim. I mean, he claims it quite explicitly.
I mean, he may not have had a general concept of what a formal system. Presumably, he knew that this worked for set theory and so on, right?
Pardon me?
Presumably, he knew this would work for set theory and so on.
I'm not sure that in the 1920s he knew Zermilo's axiom.
Oh yeah, well, that wasn't.
Was
so
Principia was his.
Okay, but the method would apply, I would suppose.
Yeah, well,
if it did exist. Right?
Yeah, he was very influenced by Lewis's survey of symbolic logic, which made the point very explicitly that you should think of formal systems in terms of symbol manipulation.
Right.
Something which. Pardon me?
That is Hilbert already. Why Lewis?
No, Lewis is first, though, you think, right? I mean,
and it was Lewis. Post didn't know Hilbert. He knew Lewis. You have to imagine the constrained atmosphere.
Yeah, it is true. I heard it maybe in that old book that says, right? Yeah. Purely formal development, whatever. Yeah. Right.
And Post mentioned in his dissertation. He mentions that quite explicitly. It's clear that it was an influence. What's his name? One of the things that comes with senility is that names disappear. The Harvard logician, the one who found the error in
Heels. Heels.
Error in what?
In the equality case.
Goldfarb.
No, not not Goldfarb, but
Drebin.
Bert
Oh,
Drebin.
the error in the proof.
Yeah.
Goldfarb proof that he was wrong. Right.
Bert Drebin studied Lewis's book quite extensively and wrote about it.
Yeah, well, I studied at Harvard. He thought Lewis, one of the great American philosophers, that was the atmosphere at Harvard.
Okay.
Right. Even though, of course, he was the founder of the evil subject of modern modal logic.
You of all people?
Well, no, I hated being at Harvard, you say, right? But, right. But that was the atmosphere, right? He was still a great figure, right? Yeah. So, yeah. I remember.
So you quoted Turing saying, "I was studying the limitations of digital computers," but this morning, Wilfred endorsed Wittgenstein's claim that Turing machines are humans who calculate. I was wondering if you would comment on the Wittgensteinian claim and whether you agree or what you think about that.
I have an absolute policy of saying nothing about Wittgenstein.
What about C? What about C? What about what C said?
Oh, I think what Zeke said was very sensible.
Amit?
I have a kind of vague question about, I'm not sure what Michael Aviv thinks, I'm not sure I understood his position, but intuitively, emotionally, when somebody tells me I have a finite device, somehow, maybe using quantum physics,
I can't hear you.
when somebody tells me I have a finite device that produces digits of a non-computable number. Okay, so I have a sense that nothing is happening here. There's a sense that there's a need to expose some, I don't know, a new concept perhaps, maybe somebody has already done this, which will tell us this is not what I wanted. This is not computation because I have no name for this number. What is happening here? Why should I call it? Yeah, so digits are being produced, admittedly, but the digits of what exactly? I mean, I could see it as interesting if there was a number definable, say, mathematically, and non-computable, which we could...
Suppose it's the fine structure constant.
It's the what?
The fine structure constant is a dimensionless number that occurs in physics.
Yeah, electron-proton mass ratio,
So-
simpler example.
Would there be a different position where we just imagine the production of a random number, and where we imagine the production of an interesting non-computable number in a sense, in a sense distinctly definable?
If it was definable, it would be.
Either physically or...
No way that I can think of to make sense of physically realizable uncomputability would be by way of a great advance in physical theory that would give us physical constants as infinite precision decimals in which that particular real number was uncomputable. And it would be a particular number. Maybe it would tell us exactly where in the arithmetic hierarchy it sits, and so on and so forth. I would think of it as a definite thing, but it's at the moment it's science fiction. No, in physical theory, it's all finite. I mean, if they get 26 places, it's a wonderful theory.
Policy of not saying anything about Wittgenstein. You answered a question I had about your lecture. You said, who wouldn't believe that the algorithm we learn in school for addition works over all the natural numbers in the same way? Of course, the answer is Wittgenstein. Now I understand why you made that comment.
Don't comment this.
Wish to say that first, on the issue raised by Professor Shapiro, and I didn't know that opposition to the conventional view went back as long as Schoenfield until you said so in print. I had always felt that the issue of Church's thesis wasn't one, that was obviously not a mathematical one or susceptible of proof or disproof, but could be a genuine problem. And I probably had in mind an axiomatic method such as discussed by Professor Sieg this morning, right, as the idea for a proposed solution. I think Friedman, whom I quoted, had that in mind too. But I'm going to give a different approach to that today, though I still think that is probably quite a viable approach. Now, I will say I've given an earlier version of this paper at just one other conference and intended to give it at the aborted version of this conference. In that conference, at least two set theorists, one said, two eminent set theorists whom I didn't ask for permission to be quoted. One one said, oh, he had always thought in this way, but didn't think there was a theorem to be stated. Another said he agreed with me, period. I have heard by some grapevine that Martin Davis here said he played around with these ideas. So I don't make any special claim. In fact, the ideas that I'm going to develop here are close to being in the original papers by Church-Turing, but are not paid enough attention to. Now, I started thinking about this more as a reaction to the paper by Saul proposing that what we've got here is a theory of computability, the term recursion theory should be abandoned, but also commending Turing's analysis as rigorous as any kind of mathematics, though not presented in any formal system. And Gandhi's extension as proving that this would apply to arbitrary machines. The technophobia that will be a dominant theme in this talk will be shown by the fact that I don't have any transparencies. Will write, if I write anything at all, on an old-fashioned whiteboard. Too bad it isn't a blackboard. And then also that, in spite of the salutary emphasis by advocates of Turing's original paper, admirers such as Gandhi and Professor Zieg, that this is a theory of human computation and that computer does not mean a mechanical device. Nevertheless, the influence of what people call Turing's analysis, or Turing's argument, and perhaps under the subtle interest of his later paper in mind that has been alluded to, has led to a computer science orientation to the problem. Whereas though my work is applied to computer science, I actually feel that I am a logician and wish to restore the logical orientation of the problem. Here I have some genuine issues with what some other people appear to write. Now, I should mention first, Saul, who wrote a paper on this in the Journal of Symbolic Logic, I have various issues with that paper, but started thinking of this as a reaction to that paper. First, he said, why don't we abandon the term recursion theory and replace it by computability theory? But I was just too used to calling it recursion theory. But also, in agreement with Professor Slayman of Berkeley, who independently feels this, I felt that the subject is as much a theory of definability as of computability. And gosh, I had a pen to write down any notes to myself if I was going to make any, but I forgot to bring it up here. Thank you. Okay, now, as far as, first, the term Turing's argument suggests that he gave one argument. In fact, as has already been alluded to, I guess in Professor Shagrir's lecture, he gave 3 in the original paper, one of which is the one generally remembered, right? And I am mostly concerned with the second one. If he really thought of himself, look, as a piece of the first argument, the analysis of, stated by Gandhi, anything computed by a human being in a routine way is Turing computable, right? The mere vagueness of the statement, computable in a routine way, and so on, seems to me to preclude calling that a theorem without such some axiomatization or something, which is what Professor Zieg was providing in his earlier lecture. Look, there were things I felt never required any axiomatization, and thus could be proved completely informally. First, there is the converse, the easier half of the theorem, supposedly denied by Church to Martin in conversation, right? That the recursive or the Turing computable functions are in fact effectively calculable. And that seemed to me sort of to be true and established and not require any axiomatization. Second, it always seemed to me, as against those who held that there isn't any actual mathematical question here, but just an explication, right? There is, after all, another thesis which might have seemed to have a lot of evidence for it in the old days. That is, the effectively calculable function should be identified with the primitive recursive functions, which, after all, were in fact called the recursive functions by Gödel, right? And Ackermann, well, before Gödel, actually disproved this thesis. Now, if and Church's thesis could be good to have been disproved, right, in this way. So if there can be a disproof, how can one say that the question of positive proof is irrelevant? I did not really understand that, even though I think most would agree that it could be disproved. Okay, nevertheless, what Turing called his argument 1, which was his analysis of how human computation can be transformed into computability on a Turing machine, to call this as rigorous as anything in mathematics has so far did, though not proved in any formal system, well, we don't need a formalization, but at least an informal axiomatization seemed to me to be a necessary thing. The idea of computed by a human being in a routine way seemed to me to be impossibly vague to call this a theorem without some further work. Okay, now I won't say anything more about that. I think as a philosopher, it was a marvelous piece of philosophical analysis. And second, did Turing really regard himself, as Gandhi and said, and others following him said, as proving a theorem? If he did, why did he give 2 other arguments? I guess 2 other proofs? You say, right. It seems to me, therefore, that this was not his attitude. And what I have to say will be very close to his second and mostly ignored proof. See, right? Now, it will also be a little bit farther away, but pretty close to the original remarks by Church, which in another paper by Professor Zieg have been sympathetically presented, though a fallacy also later found in his argument. Now, I exclude from my considerations any consideration of computability based on intuitionism or intuitionistic ideas. You know, Kreisel has raised the question of if you have a proof in an intuitionistic formal system of an existential statement, then if intuitionism is really constructive, then one must be able to calculate in some way a number given by the Gödel number of the proof in the intuitionistically sound formal system. And who knows whether this is recursive or Turing computable. See, right. Though maybe in practice it always has been. So I simply wish to exclude this problem, and intuitionism plays no role. But I will include anything that's called a calculation in the ordinary sense, and in particular, of course, except the non-intuitionistic calculation given by generating a set and its complement simultaneously as deciding the set, right? So this is not an intuitionistic problem. Now, I also wish to exclude, which is already alluded to in Martin Davis's talk, but I will still talk about it. Questions of empirically based computation. We are talking about mathematical computation, right? Okay, now, whether done by a human being or a machine or anything else. Okay, now, the basis of what I'm going to say, and an axiomatic approach is also always seemed to me to be an interesting idea, but I will state a theorem which is a simple corollary of the Gödel completeness theorem. Now, in one way it can be regarded as reducing one thesis, Church's thesis, to a special case of another one. But it also can be regarded as simply a theorem in itself about any computation that we make or imagining making today. See, right now. It is simply this. First, a computation is a special form of mathematical argument. One is given a set of instructions, okay, and the steps in the computation are supposed to follow deductively from the instructions as given. Okay? Now, so a computation is just another mathematical argument. In particular, the conclusion of the argument follows from the instructions as given, and perhaps some side well-known and not explicitly stated mathematical premises. I assume that these are all given finitely in analogy to Turing, who talked about our finite capacity. See, all right. So now the only other time I got to give this talk, which is many years ago, and maybe in honor of the country in which it was given, I called something Hilbert's thesis. I do not know now whether to ascribe this to Hilbert or to whom or when this became current, but I want to say the following is a fundamental thesis of modern mathematical logic, that any mathematical argument, and remember excluding intuitionism, but any, and in fact we don't have to look at the argument, but the statements in the argument can be formalized in some first-order language. Okay, I think this is a general belief of logicians, and a counterexample to it is an awful surprise. Okay, now, I mentioned two things. Now, computation is just a special kind of mathematical argument, and so would come under this view. See, right? Under this, that is, the steps of the computation as written should be written in some first-order formalizable system. See, right? Okay, now nothing about even whether the argument can be formalized, just the language, the meaning of the statements. Okay, if you don't believe in this thesis or doubt it, then Church's thesis has only been reduced to it in what I'm going to say. On the other hand, in Post's famous paper, recursively enumerable set of positive integers and their decisions problem, which introduced the style of using arguments informally in terms of computation, in other words, implicitly relying on the Church-Turing thesis. He then said, well, look, translation of this into a conventional formalism is a routine chore. I don't have him right in front of me to quote, but it was something like that. And look, I myself I've only heard about these students at third hand. I don't think students asked to write Turing machine programs for some bit of informal computation because it is so easy. At least it may be routine, but very laborious, right? Now, and that may be true of some of the other formalisms, but certainly it is much more routine to all logicians, anyway, to write any mathematical argument, in particular a computational one, in first-order logic, right? Now, did I say the other time I gave this paper, two distinguished set theorists talked to me, one of whom he said he had always thought of the importance of first-order logic in this way. I'm not quoting them by name simply because I didn't ask their permission, right? But he never thought there was a real theorem here. The other one said, and the real theorem is simply a corollary of a famous theorem, right? So the second theorem, the second one simply stated that he agreed with everything I said, and I hope he still does. I heard by some grapevine that Martin Davis said he had played around with these ideas. I don't know exactly what. But but as I say, these ideas are even implicit, very close to explicit in the original papers by Church and Turing. Okay, now, especially Turing. Okay, now, so, two side remarks. First, computations, especially in traditional recursion theory, often deal with partial functions. Given this, we might change conventional first-order logic to free logic, which, in spite of its obvious connection with recursion theory, has been of much more interest to philosophers than to mathematical logicians. Namely, a universal instantiation isn't except. This isn't right on it. This is right on it. Yes. Which way?
Take the top off.
Take off. Okay. Look, you know, we need a premise. There is a y such that y equals t to instantiate a given term. That is called free logic. So that might replace traditional first-order logic here. Or we can regard partial functions as having some other value u, which has a special convention for this, or just don't let function letters appear in the language. I mean, this was essentially Russell's idea in his theory of descriptions, right? Instead, always write everything out in terms of there is a unique value or just a value such as such and such. Any of these can do. Second, first-order logic for the special type of mathematical argument I'm considering is clearly much more than sufficient. Who would use in any computational argument a quantifier with lots of changes of quantifiers and ranging over all the natural numbers, some step like that? Well, maybe Kalmar, but not most of us, right? So I think a really much more restricted language suffices here. But all mathematical arguments, we might say, can be formalized in the fundamental first-order language. Now, all right, suppose we restrict oneself to first-order computations. And that just simply means that the steps in the computation, or really what needs as a first thing, only the premises and the conclusion, right, can be written in an interpreted first-order language. Okay? Now, it is fundamental to modern logic to believe that this is true of any mathematical argument, but it is also, at any rate, a routine chore in a stronger sense that it's true of the conventional formalisms, I think, to write for a logician to write any mathematical argument down in this way so that we no longer consider it to be necessary, whereas in the old days, a lot of mathematical logic was laboriously writing out all the exact formal arguments, in Frege and Kripke and so on. But now we are pretty convinced of this and don't think that this needs to be done in the same type of detail. Okay, now, given that a computation consists of some finite number of premises leading for each m to a conclusion of the form f of m equals n. And any notation for the natural numbers could be used here, like conventional decimal notation, as well as the unary notation, the stroke notation, right? The difference will make a difference to complexity theory, but of course not to traditional computability theory or Turing computability theory. Okay, now, but either way it can be used as a representation of the natural numbers or even values of other things like other formal objects, as long as they're all nameable, could be concluded. Now, given the premises of a computation, the conclusion is intuitively supposed to follow, right? Now, given the fundamental completeness theorem of Gödel, it is a simple corollary of his theorem, or special case of it, that the conclusion does indeed follow from the premises. That's what Gödel proved in his paper of 1931. See, now, what I call the first-order algorithm theorem is simply a special case of this theorem. And the idea is that any computation is a mathematical argument. Okay, now, if we find something that cannot be expressed in a first-order language, then we have a surprise not only to Church's thesis, but to the fundamental ideas of modern logic. Our attempts to formalize things failed in a spectacular way. So we, at any rate, restricting this to first-order formalizable arguments, and even neglecting the intermediate steps, right? If you have any set of premises and a conclusion of this form follows deductively, then it does indeed follow in any conventional system for first-order logic. That is Gödel's completeness theorem. The first-order algorithm theorem is simply a special case of this theorem. See, that is the argument. And so that's what I call from Church's thesis to the first-order algorithm theorem. And I say that there is a real theorem here, that any algorithm whose steps are meaningfully expressed in a first-order language, an interpreted first-order language, the conclusion of the computation for any m and n, and regardless of what notation they're written in, and what the theory is, does indeed follow from the premises. Now, there is a not so much mentioned, though indeed Professor Chagrir's paper, I think referring to Webb, did mention that there was more than one argument in Turing's paper, right? What he gives as his argument 2 in this paper is essentially that any first-order algorithm can be computed by a Turing machine as expressed in my own terminology, and actually written out by Turing. There can be little doubt that Turing would have been aware of the converse, namely that his Turing machine programs could be formalized in first-order logic, and that the steps deductively follow them. So really, what is a statement by him of an inclusion is really an equivalence.
He did it as in proving the unsolvability of...
Yes, of the Entscheidungs problem, come think of it, that's right. Okay, see, look, this is Turing's second argument for his thesis. Though the first argument, a beautiful philosophical analysis of human computation, right, requires some work to be made into anything that would be called rigorous modern mathematics, precisely the kind of thing going into by Professor Wieg in the morning. And the second argument is fine and completely rigorous mathematics, precisely as it is, right? Okay, right. Yet all attention has been focused on the first argument, never on the second and the third. The third is said to be perhaps a corollary of the second argument, or it can be a modification of the first argument. It's sort of a synthesis of the two arguments. Okay. So I think that Turing did have the first-order algorithm theorem and argued for his own Turing machine computability in terms of its equivalence, right, to the issue of a first-order algorithm. Now, Church, in his step-by-step argument, which I do looking back on Kleene, see that he does mention it, but somehow it got lost in my mind until the more recent modern discussions that revived the issue, right? And Church's argument was that in any formal system, if the formalization is such that the axioms are all recursive and each individual step of a proof has to be recursive, then the conclusions must be recursive if they're this form or recursively enumerable or whatever, right? Now, Saul says, of course, this argument contains a fallacy or a premise, because what if we discover a counterexample, a case where the steps are not recursive or computable? That's probably an objection to the way Church presents it. If this is all in first-order logic, of course, there is no such fallacy to worry about, because we know that first-order logic can be formalized in this way. All right, now, all this should be obvious, and it is indeed in the classic papers, in effect. At least Church's read in modern eyes with first-order logic is basic, right? And Turing in so many words. Yet people ignore this in favor of his first and more complicated, though undoubtedly motivationally very important, other argument. Okay, now, so far what I have to say should not really be at all controversial. Nevertheless, there does seem to me to be something controversial about it. Viz. First, it is said by Gandhi, quoting Shepherdson, and then he wrote a brilliantly elaborate paper in which, if all the terrible complexity falls into the definitions, and by the way, in defense of Gandhi's paper as opposed to Question in the Morning, I think myself that atoms, that is, elements, though not mentioned usually by the study by set theorists or conventional parts are a basic part of modern mathematics. For example, the elements of a topological space, say, are simply points, not structured object sets or something like that. Okay, but that's the subject for another discussion. Okay, so I wish to defend that part of the issue, right? But Gandhi says, and influenced by Shepherdson, an actual machine may not satisfy Turing's conditions, locality conditions, maybe many parallel computations can go on simultaneously and so on, and there are all kinds of problems, right? So then he proves an elaborate theorem that any Gandhi machine, as we might call the elaborately defined thing, and I have found great difficulty reading this paper, and Professor Zieg has made certainly valiant simplifications of it in another paper, because my own motivation was very different from that paper. I have not really hopped this all up, as they might say, right? Once you have your own view, and then you have a difficult argument based on another view, it makes it harder to read. See, right? So, now, look, what seems to me to be the case is the following. First, Gandhi cites as what might create difficulties. He talks about Conway's game of life, which really does satisfy a fairly good locality or nearness condition to the changes made. But at any rate, of the general theory of cellular automata, and maybe we'll think of something to which Turing's analysis does not apply, right? But, okay, any machine, a Gandhi machine, any kind of machine, thought of as an abstract object, it is a program. Do the steps in the program follow from the initial instructions and the program is given, or don't they? And can they be expressed in a finite, conventional mathematical language, formalizable in first-order logic, or can't they, right? If the answer is no, I don't regard this as a computation at all, right? If the answer is yes, right, then the theorem that I have just stated is enough to give an affirmative answer that the function that comes out of it must be Turing computable or recursive or whatever you want to call it, right? If not, you say this is a computation. The steps do not follow from each other, right? Or you figured out something not written in a first-order language. Well, this is an achievement. So I have not seen the need for this complicated and ingenious theorem, though others have certainly said that it is necessary once we think of simple human computation to machines. And look, you see, I don't know if you see some technophobia dominates this paper. I therefore do not use transparencies, right? I do not use any of this fancy stuff. I didn't know that my own work would actually be important in computer science, but I'm going to get away from any computer science orientation and have a purely logical orientation. So in spite of Gandhi and Zieg's salutary emphasis that Turing's theory was a theory of human computation, still the idea of machines and machine computation has come to dominate this as if this were a branch of computer science. But to me, this is a branch of logic, and I don't need any very difficult characterization of what an arbitrary machine is, as long as I assume that its program is describable in some finite language that can be formalized in first-order logic. If so, It's a corollary of the Gödel completeness theorem that the results of the computation follow from the premises of the program as given, as long as the steps are supposed to follow, and that's what is supposed to be the case, I thought, with a computer program. Okay, so what I say is not really completely uncontroversial, because in contrast to what many logicians have written, though admiring both Robin Gandy himself as both a person and a logician, and also the great ingenuity and work involved in this paper, it was very hard for me to see that it is necessary. Right. Moreover, Gandy, in order to justify his restrictions on the machine, and what he calls the most important restriction, that is the locality restriction, right, invokes special relativity, modern physics, to say that arbitrary action at a distance is not possible. Right. Now, I do not think empirical considerations belong in the subject. If they do, this becomes a different subject as to what is, in fact, empirically computable. An issue broached by the end of Martin Davis's paper, right? And I might have, and there is a considerable literature on this. Now, two comments on this. In contemporary quantum computing, the Einstein-Podolsky-Rosen paper, which established, and now, this, contrary to the intent of its lead author, seems not to be a refutation of quantum mechanics, but established as true, right, does show that correlations between arbitrarily distant states are possible in quantum mechanics, right? Now, I am not an expert on this thing. This paper, ignored for a long time, except for by people interested in quantum mechanics, and Weiss, in his Einstein biography, and he was an admirer and a student of his, positively declares this paper as of little importance, right? But now it has had a big renaissance in the modern theory of quantum computation, right? In fact, it's got a tremendous citation in the citation index. And, I actually talked to a physicist about the statement of Gandy's modern physics does not allow us. It's, well, there's modern physics and modern physics, right? Was his comment. At any rate, this empirical consideration that comes in might not even be true, right? The relation of this paradox of special relativity has been discussed. People interested in the foundations of quantum mechanics were interested in this paper, but it wasn't paid a lot of attention to in regular physics or anything else until its renaissance today, in which it's really got, is one of the top papers in the citation index, right? And things derivative are cited. So, second, once empirical considerations are allowed to come in, we have a different subject. Gandy explicitly states that he isn't going to allow analog computation, right? But it's hard to see this exclusion. Once one empirical consideration is allowed, why not? See, right? Now, by analog computation, he might be something plugging in a real number with a certain degree of uncertainty in the measurement, and another real number comes out with the corresponding uncertainty in the measurement. That's one notion of how, but there's also a result in which the calculation is discrete and digital, except on depending on a physical measurement. Suppose we take the fine structure constant, which has been mentioned, or a simpler example is the electron-proton mass ratio, right? These are precise numbers. We know little about them, right? Now, in principle, I suppose them to be arbitrarily calculable. Now, let me make some remarks about the empirical situation. For one thing, suppose time is finite in extent. If we have to write down the arguments and the values at any one time, right, then the extent of space is also important. But let's abstract from this and let the computer print out the values of a function in order, right, thus getting the arguments, and the values can take as long as he likes to print out successively, say, in conventional decimal notation, even stroke notation. Right. Now, two possibilities. One thing is whether time is finite in extent in terms of these machines. If there is a stop to them, if there is a stop, then barring what I might call a Zenonian calculation, where the calculation time gets shorter and shorter and converges, and there is a philosophical literature that claims that based on general relativity, we can have things that look Zenonian from one point of view and non-Zenonian from another or something. But anyway, excluding Zenonian calculations, right, if there is a finite limit to time and a minimum length to any computation, then the question of what numbers or what functions, Turing numbers, are computable, right, is simply meaningless, right? If not, we could assume that in principle these numbers can be measured, at least we don't know this, anything contrary, to any arbitrary degree of calculation, of approximation. This might mean calculating their decimal places, but as Brouwer already observed in his paper from the point of view of intuitionism, the 0.999 and 000 problem does mean that we can't necessarily calculate everything to an arbitrary number of decimal places. Like if something ends with 59999 or 6000, we might not know what the corresponding digit is 5 or 6. So now, as long as these numbers are not of that kind of form, we could calculate them in principle to any number of decimal places. At any rate, we could find a rational number, right, arbitrarily close to the value by actual physical measurement. At least this is not excluded. There is no physical evidence that I know of that any such number is recursive or Turing computable or whatever, and that is enough for the question. Look, many complicated examples in the whole book by Perel and Richards and so on, and Gandhi mentioned some much more sophisticated examples questioning whether physical computation, right, might lead to a non-computable number. But the simple example seems to me to show that, of course, it's hopeless to assume that, because we don't know anything about these numbers, as far as I know. See, right, I did discuss this even with one physicist. I mean, some theory might make some prediction, but we don't have any such examples. See, right, so we don't even know. By the way, I much admire, this is digression, Saul Pfefferman's great efforts to develop a more and more sophisticated system of predicative mathematics. And he then talks in side papers on scientifically applicable mathematics, which in the fashion of many philosophers of the present time he identifies with applicability to physics, though that's not the only science to which mathematics has application, actually, right? But at any rate, look, first, he has to know a lot more physics than I do to know whether scientifically applicable mathematics is exhausted by predicative stuff. There's too much physics for me. Do you really know whether string theory or whatever? See, right, but can be done in this way. But second, this simple example shows that we cannot establish that predicative mathematics is enough for physics. Because do we know this number to be hyperarithmetical? You know, to fall in the class formulated by Martin here and Mostowski and Kleene, right? We don't, as far as I know, right? See, right? So we have no idea, right? So And we certainly shouldn't add as an assumption in physics that it is. Maybe it'll turn out that some physical theory will imply that it's false. Okay, so that's enough for one idea of empirical computation. Now, there also has been mentioned something about randomness, and some paper by Shannon and others about adding a random number generator. So I make a remark about that. Look, suppose we have a genuinely random process, a quantum mechanical computation, not computation, but just a thing that emits a blip, right, every so many seconds or not, right, in a random way, which we can assume that the conditional probability given what we had before is always a half. Okay, now then, the probability that that the sequence so produced will form in any specifiable countable set, countable sets always being of measure 0, is itself 0, right? Now, the same thing goes in, and in particular, the Turing computable hyperethetical numbers, right? Second, however, right, second, however, even in classical statistical mechanics, one could get such examples as one physicist remarked to me. However, there may be hidden variables. Analysis is definitely appropriate, and the underlying processes maybe are all recursive, or maybe they aren't. See, right? Okay, see, so that could be an issue, right? Now, either hidden variables analysis of quantum mechanics making the thing really deterministic and perhaps provably recursive is possible, or it isn't. Most people don't accept such analyses. There's a majority who do hope for such a thing or even have proposed them, right? Okay, barring such a thing, right, in which the probability calculations given hidden variables analysis might not be the ultimate end of the matter, the probability is, of course, 0, that this will yield anything Turing computable. Now, I mention these empirical considerations, though they're excluded by Gandhi, since he cites modern physics. It's hard to see why other citations of empirical considerations should be regarded as irrelevant to the problem. See, right? Now, except that he excludes them by fiat. Now, to go to another paper by Gandhi on the confluence of ideas in 1936. Beautiful survey, though, as I believe Professor Ziegeschoner needs some supplementation with the role of Bernays and so on. Right, with the, is it you? Yeah.
I'm not sure.
Someone wrote a paper saying that there needs some supplementation, that Bernays' correspondence with the, with Church and so on is omitted or not emphasized enough in this paper. Was that you? Yeah, that was you. Yes, right, that was you. But, at any rate, without modification, this is a beautiful survey of situation at a certain time. And let me mention first Gandhi's quotation from von Neumann, writing in 1927 already about first-order predicate logic. So, it appears there's no way of finding a general criterion for deciding whether or not a well-formed formula is a theorem. We cannot at the moment prove this. We have no idea how such a proof of undecidability will go, right? And he goes on, right? But anyway, as today, we can't do this, right? Now, Gandhi also cites Gödel's Theorem 9 in his original paper, right? Which I think many people know today comes very close to the theorem of Church and Turing on the Church problem. That is, in any of the formal systems mentioned in Theorem 6, there are undecidable problems of the restricted functional calculus. Okay, that is a first-order logic, right? For validity is what he's talking about. All right, now then Gandhi makes some comments, of which I'll summarize this last sentence. Thus, Gödel's result meant it was almost inconceivable that the Entscheidungsproblem should be decidable, a solution could, so to speak, only work by magic. Now, then he asks a natural system, and asks why neither Gödel nor von Neumann proved the undecidability of the Entscheidungsproblem. And he has some discussion of this. This is too weak. It is certainly true that Gödel did not think of himself as having proved the unsolvability of the Entscheidungsproblem. In fact, in his later paper on the decision problem for satisfiability of statements with two existential, in pre-next form, with two existential quantifiers with a string of universal quantifiers on each side. And then he also discusses the case of 3. So he shows the first to be decidable. His statement that this applies to predicate logic with identity is now known to be false, but it certainly applies to pure predicate logic, and states that the third thing is a reduction class. If you could solve it, you could solve the complete Entscheidungsproblem. But he does not say, and we know that that cannot be done, so he certainly didn't regard himself as having proved it. But I do, had he only realized it, because look, it isn't just that it would take place by magic, a solution. Suppose there is some computation. Then couldn't you add the axioms for it to one of the systems he considers, like the set theory, Principia, and other theory, right? Won't the conclusion follow from the axioms? If so, the computation leads to a decision procedure for the Entscheidungsproblem will violate the first-order algorithm theorem, a corollary of his own completeness and incompleteness theorems is being used here. But it seems to me, indeed, to have settled the question, though neither he nor anyone else thought so. But it should have been seen as settling the question, not even coming close to settling the question, or pretty good anticipation of the word Church and Turing. It was a proof, right? But no one, including him, thought so at the time. And the most defenders of Gödel say very little work would be involved to extend Gödel's result to that of Church or whatever, right? But it isn't just that. And what Church really had was the thesis, right? I've heard negatively commented, right, on Church, right, his originality. But really, we had a solution here. And no more work was needed. No more work. Only no one realized this. No one realized this. But so I say. So I say. Now, I wish to comment. Now, there are other papers in the current literature giving proofs of Church's thesis and so on. One of the people here, I heard a paper that he read on this. It is computer science oriented, but it is based on the notion of a first order structure as developed by an earlier paper, right? And so really comes within this fundamental thesis of modern logic anyway, right? Now, now, I wish to make a further comment on what has been called by some people the intentional analog aspects of Church's thesis, or perhaps I would call the constructive part of Church's thesis. Right. First, let me call something Church's super thesis, right? Viz. That not only is every recursive function computable, right, but given any set of instructions for doing this, we can transform them into instructions post-routine drawer, right, in one of the conventional formalisms. This is easiest in the formalism of first-order logic, to which the other ones can be reduced. That is, the instructions can be transformed into instructions in first-order logic. This is not only an intentional problem, it is a constructive problem. We call this Church's superthesis. Though it is often said that ideas of effective calculability can now, given the Church-Turing thesis, be replaced, right? Anyway, from the classical point of view, by recursive function theory or computability function theory, right, as a precise explication of this, this fundamental thesis is, okay, all right, just a couple more words, is, as far as I know, not something statable in terms of recursion theory or anything like it, but is a constructivity thesis. Okay, now, however, it is a special case of formalizability of the instructions in first-order logic, in my point of view, which is an even better inventional and constructivity thesis. Now, let me call that Church's superthesis, right? Now, something else, and this is the end, I will call Church's super-duper thesis. This says that not only the instructions, but the steps in the computation can be transformed into steps in the conventional formalism. Do the Turing machine formalism, and this is pretty hard, you see. Right? It takes some work. Students don't like to do it. Right? I can attest. I have not given such problems to students, but I know others have. See, right? Okay. Formalization in terms of first-order logic is, of course, easier, right? Now, it follows from the Gödel completeness theorem that if each step follows from the instruction of the previous steps, that the resulting conditionals, right, are provable in first-order logic, right, and therefore can be formalized in first-order logic. Yet there is something missing here, which I think we all believe, right, and is done best in natural deduction systems. And the analyses of natural deduction given by Professor Prawitz and by Kit Fine may well be relevant. Look, nothing in this argument shows that there isn't all kinds of junk and intermediate steps that have nothing to do with the intuitive argument, right, in the formal proof. Gödel's theorem completeness theorem by itself does not show otherwise, right? I think we all believe in the thesis, not, I think, as far as I know, proved by anyone, though I've cited two authors whose work may be relevant, that, in fact, natural deduction systems are the best, then you could transform them into the conventional axiomatic Hilbert-style systems, right? That, in fact, a mathematical argument, and therefore particular computation, can be formalized so its steps or the steps is given, right? This is what the founders of modern logic, Frege, Russell, so on, right, believed. But I don't know if this belief has ever been proved, nor quite how to state it. It is not itself a corollary of the Gödel completeness theorem. So, I don't know whether, let's say, Church's super-duper-duper thesis, right, to the extent that the formalization should contain no irrelevant matter and actually mirror exactly the computation, has been proved. But maybe it can be either for the special case of computation or for the general case. Okay, the end.
First of all, I had a couple of logic, and where the computation is a proof in first-order logic. And
Okay, that's very helpful, yeah.
Yeah, so that has been done in great extent, in considerable detail.
Okay, yeah.
And now I want to come back. It is, of course, well known that while finding proofs in first-order predicate calculus may be hard, verifying that a certain sequence is a proof, this is automatic
Right.
in the Turing sense.
Right.
It is mechanical, if you
Right.
wish. And in fact, the first order predicate calculus was really constructed with that in mind, that proofs are automatically checkable. Now, if I don't believe in Church's Turing thesis, I can say, here I have a language, or maybe somebody will invent a logical language with proofs that are provably checkable, which are automatically checkable by means which go beyond the arsenal of Church-Turing.
Well,
So
okay, well,
you're just pushing the problem one step back.
Well, look, I have only reduced it to whether everything that can be formalized in first-order logic, right? You may not have been able to develop recursive function theory much faster than in the older days when one had to do everything in a formalism and things were very slow, right? Is justified by this because anything that we think of, we are absolutely confident that it has first-order formalization, right?
But that's sort of a roundabout argument. I say that we have no evidence that there doesn't exist a logic with rules of deduction and possibility of automatically checking proofs that goes beyond, where the process of automatically checking proofs goes beyond Church-Turing. And if there is such a system, then the Church-Turing, I mean, this is equivalent, is untrue. So we are saying the Church-Turing thesis is true because we are just looking at this logic.
Now look, I agree that we still have a thesis here. If it were false, that would be a big surprise even with a non-computational argument, right? I think logicians have had the wrong belief for years, right? At the moment, however, as I say again, the process, which might need mathematical justification otherwise, how can you just invoke Church's thesis in your proofs in recursion theory and these informal arguments and actually converting them, though a routine chore is a very tedious one, is actually a special case of what's thought of any mathematical argument in set theory or anything else using much more complicated things than computation. And this justifies it for all the existing cases. I agree that in one sense, one reduces one thesis to another and broader one. Right? Look, but something is accomplished here.
I would be equally surprised
if
the
Church-Turing
thesis is untrue, as if you would find a notion of computation which is not expressible in first order.
No, that might be true too. But you see, look, all right.
It's our
look. What I say is that, for example, I disagree with Gandhi, who saw a big problem about machines here that I cannot see really exists because he was doubting. I don't know whether his class of machines can be proved to be all doable in first-order logic or not, because I found the paper too difficult to follow. But maybe Professor Z could say something about that. If so, it would be a corollary of my argument that will work, right?
I wanted to ask you a question. There's someone ahead of you.
Yeah, okay, all right. Yeah.
I see great problem with your argument, even if you accept the thesis of the first order, because even if you can express the assumptions and the conclusion f n equal m in first order logic, and we agree that the calculation is a kind of inference, it doesn't mean it should be first order logical inference, because first order logic, what Gödel could say that every model of the premises is a model of the conclusion. And here I think we are talking about one specific model, usually the minimal model of the things. It's not clear at all. It's a logical inference. For example, if I take the Peano axiom and then somehow see that some sentence, the same language, first order language, somehow express the consistency of that system, I would say it follows from there. It follows for you. So it follows from the premises of Peano axioms, but it's not first order conclusion. So you have to convince me that the inference here, done by the computation, is a logical inference that what is true in the minimal model is true in this case will be for all models, and it might be the case, but it seems to me just equivalent to Church thesis that this inference is so simple that in fact it's logical.
Wait a minute, look, I think we do make logical inferences and no other ones. We can't get
but you also do non-logical things, like the consistency of a set of axioms, which is not logical, but still very convincing.
Well, yeah, I might something to say about that, but look, the axiom, the inferences in a computation are simply inferences. They do apply in a non-standard model because an initial segment of such a model will always be the standard model, right? See, right. So, and then we don't care what happens to the rest. See, right? Because that's not what we're concerned with. We're concerned with particular.
This is exactly what Church thesis say. That it's physical.
What?
I think this is exactly what Church thesis said. It's simple enough that it be because if it's very complicated kind of inference, then it's not going to be formulated first order logic.
No. Wait a minute. I don't know what comes. Well, look. All right. Suppose I restricted this. I think that all inferences actually made in any computation do fall under this principle, see, right? And of course, in a non-standard model, they will follow too in the initial segment, right? Which is isomorphic to the natural numbers, right? Some other things may follow concerning the non-standard model, elements of the model. We don't care about that, right? Look, the Gödel completeness theorem, there are really two things: the intuitive idea of logical inference, right, and then the model theoretic notion, right? What Gödel showed is, look, it's really an inclusion, right? Everything is in the language of first-order logic. We know that formal system is contained in follows. That's easy, see, right? Now, proving the converse is a little difficult because the notion of follows is even an intuitive one, right? But if something follows, then every model of the premises is a model of the conclusion. This is what really Gödel is. If it follows, then this must be the case. So, if you show that this is contained in this, then we don't need to give an analysis of this. They must all three coincide. At least in extension. That's what Gödel's argument really is, according to me. Right.
Yeah, I wanted to ask you a question. You mentioned that you quoted Gandhi by von Neumann. And von Neumann tried to give an argument that the decision point must have a negative slope.
Yeah.
The argument was roughly, well, if it didn't, then it would be off, because the mathematics would just be a chemical.
Yeah. Now here, of course, there is this statement.
Hardy also.
No, and I think Hardy is also quoted by Gandhi in the portion of the paper that I didn't quote. See, but of course, in one sense, that's true, right? However, perhaps the considerations in complexity theory should be taken into account, right? This Tarski's decision procedure render all the problems about geometry, elementary algebra and geometry trivial. Then there are no problems in this area. Or there's still difficult problems even though this is decidable, right? It would be the same kind of issue. Now, people certainly should have paid more attention, and von Neumann and Artie are on almost questions to what such a decision procedure would really mean, you know. It would mean, in principle, the mathematician is dispensable, but they could at least fall back on, all right, it doesn't mean it in practice. But, yeah, this was a good argument that maybe we shouldn't be so hopeful that this is true, right? Yeah, right.
Exactly. So
right.
that's the point, right? So
Yes.
when he said it explicitly, we have at the moment no idea how to prove this.
Right.
What was missing? An appropriate analysis of the notion of mechanical procedure.
Right.
So do you think he would have found your argument, even in 32, convincing?
He should have.
This is the
He should have.
Okay.
Wait a minute, when did he write? Did he write before? He wrote in 27 or
So
something.
it's such a model logic. They should do that.
27. And Gödel, of course, published in 1931 and presumably think case around 1930. And he didn't see such an argument, but I think he should have found it convincing.
Professor McCarthy and then Professor
Wait,
Aviv.
well, I think...
Did you have more?
I think
Oh,
he-
yes. So,
Go ahead.
no, but I mean, I just wanted to make a remark about the claim that because at the end there is machine analysis, that switches the subject from logic and computer science, matches the number of elements. And I don't quite understand.
Well, I don't think that was Turing's intent, but it certainly has been an effect. And of course, the later paper in mine, cited by Martin, does show that maybe he didn't like that, right? But yeah, but that wasn't his intent in the original paper.
I know.
Yes,
I mean, and Gandhi, for example, says quite explicitly.
that's right.
Turing machines just Turing, right?
No, that's right. So, you know, this result has come partly by, as you and Gandhi have rightly, even a change in the meaning of the word computer, right, from what Turing meant when he wrote in modern times, and so on. Nevertheless, this has been its practical effect, I think, is true, see, right? And because of this, there's a lot of computer science literature, right? Besides, people are fascinated by computer science and they like it, and this is the modern era. That's why I didn't use any transparencies in it. Right? You know, my opposite view of all this, right? Yeah. But look, I'd like to know what you think about my remarks on the Gandhi paper, and also whether it does or does not come within the scope of this theorem.
Well, we can discuss it perhaps.
Okay, I don't know. Yeah, because I don't understand the paper well enough that you've addressed it. Okay, right. Okay, yeah.
Professor McCarthy.
Okay.
Okay. Michael remarked on prologue as expressing things in
Okay, all right. See, so that is a legitimate computer science language. Okay. Yeah. But maybe you say something on behalf of Liz, because that's not it.
No,
yeah.
I'm not.
Okay. Yes.
At this moment. Anyway.
Yeah.
Suppose you take an ordinary programming language like Algol or Fortran. Then you can turn the program into a collection of logical sentences by the following very simple trick. You replace the variables by functions of an integer time, and you introduce the program counter as a variable which is also a function of integer time. Then you can write the program as just some sentences of logic.
Yes.
But you get a bit more from it, at least more than I think Michael claimed for prologue. At least, and that is that anything that you want to prove about the relation between the inputs and outputs of the program is a sentence of piano arithmetic which requires no principles of program correctness or anything like that. It's just it's going to end up being provable from the sentences that represent the program and the axiom system of piano arithmetic using induction if necessary.
Yeah, yeah.
Well, I think that's a sort of an illustration
Yes.
of a maybe super duper version of your
Yes. No, I think in practice the strongest version is true, see, right? But you're illustrating it, but I don't know whether it is stated, let alone proved anywhere. See, right? As I say, this is just a question in my mind, right? You know. I mean, I think that, look, before Gödel's ordinary completeness theorem, I think this was essentially believed by those who formalized quantification theory, right? But of course they had no proof of it. We probably have no proof of the strongest version, or even know how to state it, right? Yeah. I mean, we might know proof for a particular language or programming, see, right? But in general, right, for all arguments we might think of in natural language, we believe that probably don't know how to state and prove it. Yeah.
Sorry, what did you say about natural language?
You know, I mean, something in natural language. I don't know, linguistics could even be relevant here, but that we can formalize the argument in a first-order language, and the steps follow the natural steps of the argument. Though, of course, a mathematician will leave out explicit steps, right? So in that sense, the thing is false, right? That is, any formalization has a lot of detail that's just left to your mind when you read it in a mathematical proof. Even a computational proof, but much more so an ordinary mathematical proof, right?
So there is an additional problem with the, provability within predicate calculus, and that ties in with what you have said. I mean, suppose that actually the assumptions expressed in first-order functional predicate calculus about f and other auxiliary functions which are being used prove that fm is equal to n.
Yeah.
But maybe they also prove that fm is equal to n plus 7.
What do you mean?
Yeah, there
obviously, if there's a contradiction in the program,
yeah.
or the set of computation,
yeah, but
then that is bad.
But let's see what my difficulty is.
Either.
Let's see what our difficulty is. So now you give me this first order, how is it called? First order provability system for calculating f for any argument values. And now I follow you blindly, I believe you, and I get that fm is equal to 32, and I have no idea whether fm might also not come out to be 100 to, taken to the power 100,000.
No. Like any
and
inconsistent,
be sure.
Like any inconsistent system, an inconsistent set of computations,
yes.
Right?
Yes.
Now, look. This can either be disallowed by fiat. I mean, this problem arises in the Herbrand-Gödel formalism. It does not arise in Turing's formulation, but suppose Turing's formulation allowed, non-deterministic or branching computations, right? He easily could have, see, right? And of course, in complexity theory, the equivalence of this is a big problem, but it's not a problem in Turing computability as long as the result is the same, right? But otherwise, there might be an inconsistency in the computation. So, yeah, any set of instructions for a computation might be inconsistent It's if we believe that they are consistent with this argument is valid, but that happens. That happens for anything.
That's true. So maybe we have to maybe we have to add the provision that we get the answer and we are certain of it.
Well, yeah, okay.
That would be a very reasonable real-life position.
If one were really worried about this, one could choose, say, the leftmost path in the Turing branching computation, or the thing with the least Gödel number, or whatever, in the first order computation, or run Gödel computation. This is not really the biggest problem in the world, I believe, right? Except from the point of view of complexity here. Right.
Well, actually, it's much simpler.
Yeah.
Namely, in the system that I described of formalizing algo programs, it's guaranteed to be consistent because the formulas are all of the form a variable at time t plus 1 equals something in terms of values of the variables at time t.
Okay. Okay. Now, to believe that things for which the consistency is guaranteed, like the non-branching Turing formulation and such a thing, right? The uniqueness of the result. But it isn't really a big problem, even if the consistency is not guaranteed.
We have time for one last question.
Yes. I've heard throughout the day people trying to prove the Turing thesis. Turing himself said that the word proof is inappropriate. It would be much more appropriate to call it propaganda. So
where you say that? Oh, that's interesting.
Oh, I'll have to look it up.
That's contrary to later interpreters.
Well,
right. Yeah.
Well,
you're not confusing Turing with Google?
No. I actually, I'm pretty positive about it because the person who wrote the only book about Turing that I ever read is sitting here right in front of me, and it's probably coming from him, and I quite trust him. Am I right?
He did use the word propaganda.
Oh yeah.
Yeah, he said propaganda is more appropriate to.
That is I can tell you where it is. It's in this wonderful informal exposition of solvable and unsolvable
That's it.
problems.
Yes.
Thank you.
Oh, okay. Well.
So let's not prove it.
Yeah. Now look, he
propaganda. Are you against propaganda?
No, I agree.
can't believe his argument too, as stated. Well, what it proves is a proof. Period. Right. Number two. Number one, I think, has a lot more work to me other than sort of a convincing philosophical analysis. Right. But maybe the work has now been done. See, right. That is interesting. I was unaware of the quote. Right. Okay. Yeah.
Thank you.